Hi, everybody. Welcome back to our NSX 4.0 tutorial. So in previous lessons, we're just finished talking about the whole NSX switching and also some of the fundamental, for example, the basics and the components, architecture, sort of things. So today, we're going to talk about NSX routing. So I'm so excited to start a new session because NSX routing is a little bit crucial for the whole NSX system design and also implementation of NSX. Let's get right to it. Firstly, we're going to talk about logical router. When we look at logical router, we think about physical router, physical routers. So I bet everybody is familiar with physical router, even it's no matter what size it is, which is if it's small or if it's medium size or large, it is physical router. But in an NSX world, we talk about logical router. So logical router's function is pretty similar to a physical router. So it just provide us east-west routing, which is inter-segment, or previously we call it inter-VLAN routing. Now here we inter-segment routing, which is east-west routing or NS north-south routing, which is the traffic that we're talking about, the traffic that coming in the NSX system and going out of the NSX system, which is the north-south traffic. And also we provide a lot of networking services, for example, NAT, load balancer, firewall, and also VPN, VRF, so many other functions, DHCP, so many features that are based on the networking. So here we just give you an example of logical router, because here we have two segments, and we also have some of the VMs, and just the purpose we want those VMs to talk with each other. So why a routing function? Because here there are two subnets. So in terms of communication between the two subnets, we have to use a routing function, which is a layer 3 routing, IP routing. So that means when this VM send out the packet will go to their gateway at the first step. So here's the gateway. Here's a blue segment's gateway. So that means we just route the traffic from the green to the blue one. So that's traditional routing. Yeah. For logical routers, we also provide NS routing. That means some traffics will go out of the data center or go out of the NSX system. This is the NSX system. if traffic wants to go out of NSX and also the traffic goes into the NSX system, we need logical routers function to interconnect with the physical router via a segment. This is the interconnection segment. I also have some terminology, but it's not very critical for you to understand the whole system. For example, downlink means to downlink to the VMs, and uplink generally we call uplink. That means this link will go to physical router. That's it. So let's take a close look at the logical routers. So there are two components under or within the logical router. DR, distributed router, and services router or service router. Why do we have these two? Because when we look at the physical routing, we just have routing. We just have one router, a concept of the routing or router. But here, and for NSX, we have a distributed router and services routers. So because NSX is a software-based network, so we have to handle distributed transport node, right? We have a lot of ESXi hosts, and we have a lot of distributed transport node where there's vSphere kernel, NSX kernel, or we can call it hypervisor for a distributed on every transport node. So we have to handle this, and we'll also handle some of the centralized services. For example, northwest, right? Northwest traffic routing. So some of the services or some of the function are or have to be centralized. Some of the functions have to be distributed onto the every transport node. So here we have distributed form factor. We also have services router form. So for distributed router, the function that runs locally in the every transport node, participating in the NSX fabric. But what is an NSX fabric? I think you just remember this sentence: runs locally, distributed in the every transport node, because it's distributed. And also you just the function provides distributed EW routing, and we'll get into it this in a couple minutes. And also for service router, just that means we have a lot of centralized routing or network function or network services that provides, and for example, NS routing and services, NAT, BGP, or gateway firewall. So this SR or services router, the function lives in or lives on an edge node. Just remember that. Just be careful. This is very important. SR as a centralized point always live on a container. For example, edge node VM is a container. Edge node bare metal is also another container. So always lives on a container. But a distributed router lives on every transport node. Okay. So why we need distributed router, or why we need distributed routing function? Here we just demonstrate this, and so here we have a logical router, which is a green one. We have two segments with 4 VMs. And the VMs are setting on a different ESSi host. So when we created, after we created the logical router, which is a logical function on the NSX configuration UI, and then the whole function will be distributed or allocated to every transport node. So that means we have a DR, distributed router. We have DR, the same function components are distributed to every transport node. So for Sunday, this VM wanted to talk to this blue VM. How did it go? So you just send out a traffic to this DR, to this, because this closest distributed router that is setting on this ESSS1 host. So then the traffic is directed to the blue one locally. So you can please, I think you notice that all traffic will be locally within the ESSS1 host. There's no chance to go out and to this one logical router. It seems like there's a centralized node, but the traffic doesn't go out and coming in again. So this is what DR is for. So that's deal with the local forwarding, right? I think you got what I mean. So another example is when we want this VM to communicate to this VM, which is located in the ESSi2. So that means we have to go through this DR, because they are two subnets. We have to go through a routing function. So here we have to go through this DR in this case, and then to this DR will check this routing table and see the next hop. So here next hop is locally directed segment. So so that means the routing function is finished, and then we have to deal with switching or encapsulation of switching, how to send out the traffic onto the blue segment. So that means here we have to go beyond the local ESSi host to another host, ESS2, which is ESS2. So we have to prepare for the encapsulation, which is the Geneva tunnel, to to have the whole traffic get to the destination. That's the whole process. And in the opposite direction, when the traffic, when the blue one wants to communicate to the, when the blue wants to communicate to the green one, they have to go through this DR. So you can see the difference as compared to physical routing. The DR is chosen the nearest DR is always chosen for the traffic forwarding or traffic routing. Just remember, there's a rule of thumb. The closest DR will be chosen for the traffic forwarding or a traffic routing. So you can see that the two directions traffic will choose different DR. Okay, that's why or what the DR is all about. This is an NSX. I think it's a advantage of an NSX system because they at the beginning they cares about how local traffic or how all of the traffic traverse. So let's talk about SR. So as I said, SR is a centralized point that where we can handle the centralized services. For example, here we have a lot of centralized services that you can distribute to the SR. So just those services or those modules that are not able to allocate to the distributed transport node will allocate to SR. That means those services are, have some of the property or attributes of centralization. They have some centralized action or properties for this function to operate. So we just allocate them to SR. For example, we have a northwest routing. We have a PV gateway. This is a bridging. This is a bridging logo, and also NAT load balancing, some gateway firewall, VPN. Those are centralized services. We have to have them live on the edge node. Edge node has, edge nodes have two types. One is VM, one is bare metal. So edge nodes, yeah. Edge nodes are appliances with a pool of capacity for hosting any centralized services which are not distributed. So that means edge node is a container. Containers. They have two types, VM and bare metal. Most of the time we talk about edge node, we talk about VM edge node. How do you set up VM edge node? You can make it via NSX UI, edge node transport edge transport node preparation preps. There's a particular UI for you to install edge transport node. under the hood, they have a OVA and just import it to a Agile VM, and also have an ASO installation file for bare metal setup or installation. For example, if you have a performance request, or very high performance request, for example, NFV, or for use in a service provider environment, you can set up bare metal Edge node for better performance. Yes. So for Edge node, in terms of sizes, we have 4 sizes: small, medium, large, extra large. In terms of CPU and memory, or some other physical limits. We also have a DPDK concept in here. So for quick forwarding, for example, when we configure the edge node, transport node props, we can see the configuration, which is a fast path interface for DPDK. DPDK fast path interface 1, 2, 3. What does that mean? I think we'll get into that in coming sessions when we talk about NSX design. We'll talk about this fast path interface 0, 1, and 2. Here is that's the sizes. So different versions NSX have different limits. So please refer to the document to see the limitation or restriction, or just physical CPU and memory. For example, you're planning a POC, you have to give some of the limits and physical requirements, physical server requirements for to the customers. So let's take a look at a logical routing topology. This is very just illustrating the how real traffic is going, or how they go through every component. So for example, we already talked about DR. DR is distributed down to every hypervisor, every TN, right? TN. So we have a lot of production VM here, VMs here. So this so for this two rack, we just label them compute, or just set up them into the compute cluster. And for this two racks, we plan them to be infrastructure clusters. So that means we put edge node VM onto this physical server. We also have vCenter, NSX manager. So those VMs are for management uses, and also edge node for routing uses. That's it. This is a typical production environment, or when it comes to design of the whole NSX system. The traffic, real traffic, will be, for example, from this VM, go through the physical cable to the spine, to the span switches, which you can access switches, access switch or TOR switches, TOR top of rack switches, sorry. And then it goes to another infrastructure cluster physical server. And logically, the traffic is headed to the logical router or just edge node. Then edge node will send out the whole traffic to the outside world, to the outside. This is a physical router. Okay, so you can see that traffic will go zigzag, like a zigzag, and to finally go outside. So you don't worry about the performance of the physical connection or physical switches, because the capacity with the physical switch is way much higher than you would expect it. Okay. And another one is when we talk about logical routing, when we talk about NSX routing, we have two infrastructure, where we have two topologies. One is a single tier. Single tier means we have, for example, as illustrated here, we have physical router. Outside, and we have a logical router. It's a one tier or single tier logical router. We call it tier 0 logical router. And we just attach all of the VM directly to this logical router logically, right? So that's a single tier routing. So that means every VM, when they want to talk with each other, they just go through one tier of router and then go to the destination. That's a single tier. But when we zoom into the LR, we can see the detailed one. As I said, so every logical router has two components, DR and SR. So when we zoom into the tier 1 or T0 LR, we have DR and SR. DR will locate it onto every TN, and SR will be sitting on the edge node. So what about the interconnection with SR and DR? There's an interconnection, which is internal. So you don't care about the anything about internal segment or a logical switch. NSX will handle this automatically. For example, they just automatically assign the IP address to this internal connection. You don't need to worry about that. Just when you think about the whole topology, you just, there's a link, there's a subnet between SR and DR. That's it. So SR had this routing table, and DR also had this routing table. So when you analyze the whole traffic routing, just follow your previous experience on routing table, MAC table, forwarding table sort of things. So you can even show routing table on the edge node. So that's a single tier. So logical routing. So this is the start of packet forwarding process. We have a lot of packet forwarding processes in a later chapter, but this is the very beginning of it, and which is the simplest one. For example, we have this VM wants to talk to another server outside. Another server. This is the destination. So they just this VM just send out this payload, and the source IP is its own IP, and destination is this IP 192.168.10.1. Yeah. When the packet goes into the hypervisor, goes into this TN hypervisor, it just look into this payload and check and look up all of the the NSX tables that I taught you. So here's the DR. So for example, when they have a inter subnet traffic, the traffic has to go through their gateway, right? So the first step is the DR, which is the place the gateway and default gateway or distributed default gateway is sitting. So you just check the DR routing table and to find out where the 192.168.10.1 is. So you just match this one, match 0000. So the next hop will be 169 to 258 or and 0.2, which where is it? It's right here, right? This is the SR's interface IP, right? So that means DR will send out the traffic, send out the packet via this transit logical switch, right? This is internal, automatic created transit logical switch to SR. That means we have DR SR connection, right? I just talk about this is the internal transit segment. So packets now is here, and within this step, they just this transport node or hypervisor just checked. The purpose is we want to transmit this packet to SR, but SR is on another TN, right? Another physical server. So we have to prepare myself to do the encapsulation, to do the tunnel transportation, right? So that means we have to check the forwarding table to this is the forwarding table. So how to reach to the this 0 to 0.2. So we have to have a Geneva tunnel encapsulation. So that means we send out the Geneva encapsulation, and then to the to another TN. So by decapsulating the tunnel tunnel, and the original payload is here and goes to the SR, then still look up the routing table and see the next action. That means to go to go through this interface or this IP. So then they send out the packet to the outside router. So that's the whole process for the traffic from this VM to outside VM. So you can see the whole process were just by leveraging the DR function, by leveraging the SR function, by leveraging the Geneve tunnel, we made the whole process. Okay. And in the reverse direction, I think the same thing happened, but there's a little bit difference here. For example, we have a payload, and the payload will send out to this NAS hop, this IP as a NAS hop by physical router. Physical router will send out this payload to the SR. When SR got this payload, and look at the routing table and to see where 10.1.1.0 is located, and the next hop is 169 to 54.01. Where is it? Is it on this DR? So when we think about routing a DR, we just NSX always leverage or always use the closest DR as a routing node, as a router. They just there's a local DR, they send out to the local DR. This DR will in turn look up the routing protocol and look up forwarding table to see 10.1.1.10's location. In this case, 10.1.1.10 is directly connected, right? From routing point of view, is not locally, directly connected subnet. From routing perspective, but when they check the forwarding table, that means how we reach out to this VM, how the packet goes out and go to the destination. They have to use a Geneve tunnel because the destination VM is on another transport node, so they have to do the Geneve tunnel, encapsulate the Geneve tunnel, then send out the Geneve encapsulation and to the final TN, and then goes to the final VM. That's the reverse direction. So you can see that the packet coming in, packet going out, that follow different paths. When it comes to DR, also the path goes to the different interface. right? So you can just go back to compare these two processes. And that means I just give you a rule of thumb. That means in the NSS world, always do routing as early as possible. NSS does routing function as early as possible. As early as possible, then what? Then switching. Switching mainly means encapsulation or just build up a Geneve tunnel. So always do routing earlier than switching. And the second rule of thumb is always leverage closest DR or closest router. In terms of, from packet forwarding perspective, always use closest DR or always use closest router. We don't use this. This is not closest DR, right? When packet is here, we always use our local DR as a closest DR for routing function instead of using this distance one. Okay, that's a rule of thumb, two rule of thumb. You can just I just give you a feel of that just by learning more and experimenting more. You can have your touch on it. And then when it comes to dynamic routing protocol, so we just don't teach you any routing protocol, because when you think about physical routing or CCIE certification of networking, we always talk about routing protocol. Routing protocols are the meat of networking. But NSX as SDN, within NSX system, we have a lot of particular tables, so NSX can manipulate and help us do some routing and switching. So you don't need to have or you don't need to care about the routing protocol within NSX. And here we just bring up this. Let's give you how to connect with a physical router. So here's a physical router 1, here's physical router 2, here's the NSX, right? Below is NSX, right here. So we have logical router, right? Do we have to have only one logical router? I have a question for you here. So when it comes to redundancy, you have to have at least 2, right? So that's mean we just come up with another topic, which is HA of our logical routers. We'll talk about that in a bit later. And for logical router and a physical router, here's a standard link, right? Subnet, we call it uplink. We always call that uplink. So uplink, for uplink, we have the next hop IP address. We have IP address here. in our local site, local site. There's a remote site. So we have at least 2 subnets right here, and with at least 30 network mask. That's it. And we just running static route, BGP route, OSPF on this link, on these links, right? They also have ECMP, equal cost multipath. We can handle 8-way ECMP because, for example, there's 8, there's only 2, right? We have at most 8-way ECMP for traffic distribution. We also have BFD as a supplement for fast detection or convergence. When they talk about convergence and detection, this is 2 things. Detection means we have physical failure happened on the underlay layer. For example, layer 1 failure, layer 2 failures, a switching failure, or lane failure. So how do we detect it quickly? And when it comes to convergence, we have to call on routing protocol. That's a dynamic routing protocol. For example, OSPF. Here we have hello time, hold on time, retry sort of things. So it's for ensure our for our convergence mechanism. So, but it is a little bit slow for a particular application or environment. So that's the BFD come into play. So BFD has a quickest hello time is 300 millisecond, and for bare metal edge node, and 1 second for VM edge node. So you just continuously send out hello, keep live, keep live, keep live. So that's a BFD mechanism. It's just a supplement for the routing protocol to help us to carry out fast detection and convergence. Okay. So when it comes to BFD at BGP, sorry, BGP has a lot of stuff to talk about. It's attributes, decision making process. When you just refer to the Halabi Bible for CCIE exam, which is Bible book for BGP. Here, I think the dynamic protocol did not change for 20 years. So it's AS-path prepending, MED, weight, local preference, community. So you can use a lot of pretty old school attribute to manipulate the whole BGP decision. Yeah, that's all of the things you can configure in the NSX. But for enterprise uses, they're not very complicated as compared to server provider or internet backbone. Okay, pretty easy. And also OSPF, we also have OSPF for inter or intro area. We support multiple areas scenario for OSPF. And also support So, you know, the type 1, type 2, type 3, type 4, type 7, 5, or 7, those kind of, you know, the OSPF database when in terms of, you know, OSPF mechanism, and there are a lot of books that are good books about OSPF. Yeah, that's it. That's everything for this lesson. In next lesson, we'll talk about the two-tier or multi-tier routing, and just give you another or other forwarding process for the whole routing procedure. So thank you. I hope you enjoy it. And if you have any questions, just let me know. Leave some comment, and please like it, and share it with your friends. I'll see you in the next lesson. Bye.